This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Relativity, the Special and General Theory by Albert Einstein. Continuing Part 2, The General Theory of Relativity, Sections 27 to 29. Section 27. The space-time continuum of the general theory of relativity is not a Euclidean continuum. In the first part of this book, we were able to make use of space-time coordinates, which allowed of a simple and direct physical interpretation, and which, according to section 26, can be regarded as four-dimensional Cartesian coordinates. This was possible on the basis of the law of the constancy of the velocity of light. But according to section 21, the general theory of relativity cannot retain this law. On the contrary, we arrived at the result that according to this latter theory, the velocity of light must always depend on the coordinates when a gravitational field is present. In connection with a specific illustration in section 23, we found that the presence of a gravitational field invalidates the definition of the coordinates and the time, which led us to our objective in the special theory of relativity. In view of the results of these considerations, we are led to the conviction that, according to the general principle of relativity, the space-time continuum cannot be regarded as a Euclidean one, but that here we have the general case, corresponding to the marble slab with local variations of temperature, and with which we made acquaintance as an example of a two-dimensional continuum. Just as it was there impossible to construct a Cartesian coordinate system from equal rods, so here it is impossible to build up a system, or reference body, from rigid bodies and clocks, which shall be of such a nature that measuring rods and clocks, arranged rigidly with respect to one another, shall indicate position and time directly. Such was the essence of the difficulty with which we were confronted in section 23. But the considerations of section 25 and 26 show us the way to surmount this difficulty. We refer the four-dimensional space-time continuum in an arbitrary manner to Gauss coordinates. We assign to every point of the continuum, or event, four numbers, x sub 1, x sub 2, x sub 3, and x sub 4 coordinates, which have not the least direct physical significance, but only serve the purpose of numbering the points of the continuum in a definite but arbitrary manner. This arrangement does not even need to be of such a kind that we must regard x sub 1, x sub 2, and x sub 3 as space coordinates and x sub 4 as a time coordinate. The reader may think that such a description of the world would be quite inadequate. What does it mean to assign to an event the particular coordinates x sub 1, x sub 2, x sub 3, and x sub 4, if in themselves these coordinates have no significance? More careful consideration shows, however, that this anxiety is unfounded. Let us consider, for instance, a material point with any kind of motion. If this point had only a momentary existence without duration, then it would be described in space-time by a single system of values, x sub 1, x sub 2, x sub 3, and x sub 4. Thus, its permanent existence must be characterized by an infinitely large number of such systems of values, the coordinate values of which are so close together as to give continuity. Corresponding to the material point, we thus have a unidimensional line in the four-dimensional continuum. In the same way, any such lines in our continuum correspond to many points in motion. The only statements having regard to these points which can claim a physical existence are in reality the statements about their encounters. In our mathematical treatment, such an encounter is expressed in the fact that the two lines which represent the motions of the points in question have a particular system of coordinate values, x sub 1, x sub 2, x sub 3 and x sub 4, in common. After mature consideration, the reader will doubtless admit that in reality such encounters constitute the only actual evidence of a time-space nature with which we meet in physical statements. When we were describing the motion of a material point relative to a body of reference, we stated nothing more than the encounters of this point with particular points of the reference body. We can also determine the corresponding values of the time by the observation of encounters of the body with clocks, in conjunction with the observation of the encounter of the hands of clocks with particular points on the dials. It is just the same in the case of space measurements by means of measuring rods, as a little consideration will show. The following statements hold generally. Every physical description resolves itself into a number of statements, each of which refers to the space-time coincidence of two events, A and B. In terms of Gaussian coordinates, every such statement is expressed by the agreement of their four coordinates, x sub 1, x sub 2, x sub 3 and x sub 4. Thus, in reality, the description of the time-space continuum by means of Gauss coordinates completely replaces the description with the aid of a body of reference, without suffering from the defects of the latter mode of description. It is not tied down to the Euclidean character of the continuum which has to be represented. Section 28. Exact formulation of the general principle of relativity. We are now in a position to replace the provisional formulation of the general principle of relativity given in section 18 by an exact formulation. The form there used, quote, all bodies of reference, K, K prime, etc., are equivalent for the description of natural phenomena, or formulation of the general laws of nature, whatever may be their state of motion, unquote, cannot be maintained, because the use of rigid reference bodies, in the sense of the method followed in the special theory of relativity, is in general not possible in space-time description. The Gauss coordinate system has to take the place of the body of reference. The following statement corresponds to the fundamental idea of the general principle of relativity. All Gaussian coordinate systems are essentially equivalent for the formulation of the general laws of nature. We can state this general principle of relativity in still another form, which renders it yet more clearly intelligible than it is when in the form of the natural extension of the special principle of relativity. According to the special theory of relativity, the equations which express the general laws of nature pass over into equations of the same form when, by making use of the Lorentz transformation, we replace the space-time variables x, y, z and t of a Galilean reference body K by the space-time variables x prime, y prime, z prime and t prime of a new reference body K prime. According to the general theory of relativity, on the other hand, by application of arbitrary substitutions of the Gauss variables x sub 1, x sub 2, x sub 3 and x sub 4, the equations must pass over into equations of the same form. For every transformation, not only the Lorentz transformation, corresponds to the transition of one Gauss coordinate system into another. If we desire to adhere to our old-time three-dimensional view of things, then we can characterize the development which is being undergone by the fundamental idea of the general theory of relativity as follows. The special theory of relativity has reference to Galilean domains, i.e. to those in which no gravitational field exists. In this connection, a Galilean reference body serves as body of reference, i.e. a rigid body the state of motion of which is so chosen that the Galilean law of the uniform rectilinear motion of isolated material points holds relatively to it. Certain considerations suggest that we should refer the same Galilean domains to non-Galilean reference bodies also. A gravitational field of a special kind is then present with respect to these bodies. Cf. sections 20 and 23. In gravitational fields there are no such things as rigid bodies with Euclidean properties. Thus the fictitious rigid body of reference is of no avail in the general theory of relativity. The motion of clocks is also influenced by gravitational fields, and in such a way that a physical definition of time, which is made directly with the aid of clocks, has by no means the same degree of plausibility as in the special theory of relativity. For this reason, non-rigid reference bodies are used, which are as a whole not only moving in any way whatsoever, but which also suffer alterations in form ad lib during their motion. Clocks, for which the law of motion is of any kind, however irregular, serve for the definition of time. We have to imagine each of these clocks fixed at a point on the non-rigid reference body. These clocks satisfy only the one condition, that the readings which are observed simultaneously on adjacent clocks in space differ from each other by an indefinitely small amount. This non-rigid reference body, which might appropriately be termed a reference mollusc, is in the main equivalent to a Gaussian four-dimensional coordinate system chosen arbitrarily. That which gives the mollusc a certain comprehensibility as compared with the Gauss coordinate system is the really unjustified formal retention of the separate existence of the space coordinates as opposed to the time coordinate. Every point on the mollusc is treated as a space point, and every material point which is at rest relatively to it is at rest, so long as the mollusc is considered as reference body. The general principle of relativity requires that all these molluscs can be used as reference bodies, with equal right and equal success in the formulation of the general laws of nature. The laws themselves must be quite independent of the choice of mollusc. The great power possessed by the general principle of relativity lies in the comprehensive limitation which is imposed on the laws of nature in consequence of what we have seen above. Section 29. The solution of the problem of gravitation on the basis of the general principle of relativity. If the reader has followed all our previous considerations, he will have no further difficulty in understanding the methods leading to the solution of the problem of gravitation. We start off on a consideration of a Galilean domain, i.e. a domain in which there is no gravitational field relative to the Galilean reference body K. The behaviour of measuring rods and clocks with reference to K is known from the special theory of relativity. Likewise the behaviour of isolated material points. The latter move uniformly and in straight lines. Now let us refer this domain to a random Gauss coordinate system or to a mollusc as reference body K'. Then, with respect to K', there is a gravitational field G of a particular kind. We learn the behaviour of measuring rods and clocks, and also of freely moving material points with reference to K', simply by mathematical transformation. We interpret this behaviour as the behaviour of measuring rods, clocks, and material points under the influence of the gravitational field G. Hereupon we introduce a hypothesis that the influence of the gravitational field on measuring rods, clocks, and freely moving material points continues to take place according to the same laws, even in the case where the prevailing gravitational field is not derivable from the Galilean special case, simply by means of a transformation of coordinates. The next step is to investigate the space-time behavior of the gravitational field G, which was derived from the Galilean special case simply by transformation of the coordinates. This behavior is formulated in a law which is always valid, no matter how the reference body, or mollusc, used in the description may be chosen. This law is not yet the general law of the gravitational field, since the gravitational field under consideration is of a special kind. In order to find out the general law of field of gravitation, we still require to obtain a generalization of the law as found above. This can be obtained without caprice, however, by taking into consideration the following demands. A. The required generalization must likewise satisfy the general postulate of relativity. B. If there is any matter in the domain under consideration, only its inertial mass, and thus according to section 15, only its energy is of importance for its effect in exciting a field. C. Gravitational field and matter together must satisfy the law of the conservation of energy and of impulse. Finally, the general principle of relativity permits us to determine the influence of the gravitational field on the course of all those processes which take place according to known laws when a gravitational field is absent, i.e., which have already been fitted into the frame of the special theory of relativity. In this connection, we proceed in principle according to the method which has already been explained for measuring rods, clocks, and freely moving material points. The theory of gravitation derived in this way from the general postulate of relativity excels not only in its beauty, nor in removing the defect attaching to classical mechanics, which was brought to light in section 21, nor in interpreting the empirical law of the equality of inertial and gravitational mass, but it has also already explained a result of observation in astronomy, against which classical mechanics is powerless. If we confine the application of the theory to the case where the gravitational fields can be regarded as being weak, and in which all masses move with respect to the coordinate system with velocities which are small compared with the velocity of light, we then obtain as a first approximation the Newtonian theory. Thus the latter theory is obtained here without any particular assumption, whereas Newton had to introduce the hypothesis that the force of attraction between mutually attracting material points is inversely proportional to the square of the distance between them. If we increase the accuracy of the calculation, deviations from the theory of Newton make their appearance, practically all of which must nevertheless escape the test of observation, owing to their smallness. We must draw attention here to one of these deviations. According to Newton's theory, a planet moves around the Sun in an ellipse, which would permanently maintain its position with respect to the fixed stars, if we could disregard the motion of the fixed stars themselves and the action of the other planets under consideration. Thus, if we correct the observed motion of the planets for these two influences, and if Newton's theory be strictly correct, we ought to obtain for the orbit of the planet an ellipse, which is fixed with reference to the fixed stars. This deduction, which can be tested with great accuracy, has been confirmed for all the planets save one, with the precision that is capable of being obtained by the delicacy of observation attainable at the present time. The sole exception is Mercury, the planet which lies nearest the Sun. Since the time of Leverrier, it has been known that the eclipse corresponding to the orbit of Mercury, after it has been corrected for the influences mentioned above, is not stationary with respect to the fixed stars, but that it rotates exceedingly slowly in the plane of the orbit and in the sense of the orbital motion. The value obtained for this rotary movement of the orbital ellipse was 43 seconds of arc per century, an amount ensured to be correct to within a few seconds of arc. This effect can be explained by means of classical mechanics only on the assumption of hypotheses which have little probability, and which were devised solely for this purpose. On the basis of the general theory of relativity, it is found that the ellipse of every planet round the Sun must necessarily rotate in the manner indicated above, that for all the planets, with the exception of Mercury, this rotation is too small to be detected with the delicacy of observation possible at the present time, but that in the case of Mercury it must amount to 43 seconds of arc per century, a result which is strictly in agreement with observation. Apart from this one, it has hitherto been possible to make only two deductions from the theory which admit of being tested by observation, to wit, the curvature of light rays by the gravitational field of the Sun, first observed by Eddington and others in 1919, and a displacement of the spectral lines of light reaching us from large stars, as compared with the corresponding lines for light produced in an analogous manner terrestrially, i.e. by the same kind of atom, established by Adams in 1924. These two deductions from the theory have both been confirmed. End of section 29.